Okay, this is weird. So first of all, we're the only ones here. Second of all, where are we? I know we're used to seeing a whiteboard, and here I have a chalkboard, which is better in my opinion. Anyway, as you probably know by now, we no longer have face-to-face meetings in classrooms, but since I record my lectures, I decided that I would continue to do so and follow up with questions in the next lecture. So, as I already explained in an email to my class, what I'll be doing is I will be posting lectures, the lectures that I would have given anyway in class, and basically you will either, if you don't understand something or you need me to clarify something, you would drop it down in the comment section or email me through Jupiter Grades, which you should have access to by now, and I will address any questions or issues or concerns and make any clarifications in the next video. Yeah, that's kind of the plan moving forward indefinitely, unless something else comes up that's better. For me, just for my teaching style, I think anything like Blackboard, Collaboration, Ultra just kind of wouldn't work. It would feel very awkward. We still have some awkwardness since I'm here by myself talking to myself. It's very lonely and very strange, and I've never done this before. And we're in a completely different location, obviously, because the whiteboard had glares that I didn't like, and so I prefer to write on chalkboards anyway. So that being said, we're actually going to jump straight into it. So we are continuing Math 1203, lecture, I want to say 21, but never mind that. We're just going to pick up where we left off. Last time I gave you a handout, related rates. This is what we're going to actually do today. And we are going to be doing this for the next 50 minutes, because that's how long a class lecture would take. So I don't have anyone to ask questions, but we'll make it. Okay, so last time I gave you guys this handout. If you're in my class, of course, it is on the class webpage. I'll also probably post a link in the video description just to make it easier to access if you don't have access to it. But the next topic on our agenda is related rates. It is an application of derivatives. Particularly implicit differentiation. And the idea is the following. Sometimes we know about related quantities in various forms, and we want to know about rates of change in response to this. So the idea is if quantities are related, right? And in math, when we're talking about relationship, we mean that there's some kind of equation or formula that connects all these quantities. And like I said, quantities can refer to various things. We're going to see many examples. But if quantities are related, it turns out so are their rates. And how would we get a relationship between the rates of change of the quantities if we know about the relationship between the quantities themselves? Simple. Implicitly differentiate the relationship. And that's going to allow us to talk about rates whenever we know about the quantities themselves. And so the idea is if some rates are known, we may be able to find others. Right? So that is basically the idea. So we have a relationship between several quantities, two or more, and we automatically, by knowing the relationship between the quantities, we will automatically know relationships between their rates. And the idea being, if I know about the rate of change of some of the quantities, I can figure out the rate of change of other quantities. And this can be very useful. So we've seen examples before, like van der Waals equation, which relates the volume and the pressure of a specific gas. So the van der Waals equation actually gives us a relationship between pressure and volume. And so we might want to know, well, if the pressure is changing at a certain rate, how fast will the volume change in response? So a question like that would be a question that we answer with related rates. So that is the idea. In fact, this is one of several types of word problems that we will be looking at. And so it's kind of important for you to recognize when you are looking at this kind of problem. So for example, we have seen exponential growth and decay problems earlier, and we know some of the key terms that tells us that that's the kind of problem we're looking at. So if you see like radioactive, if you see something growing proportional to its size, and things of that sort, you know that it's exponential growth and decay problem. How would you know that you're looking at a related rates problem? How do you know? Is the first thing you're going to want to be able to identify. So if you're doing a quiz or a test or something like that, there are several different word problems on the quiz. You might want to know, well, which one of these is a related rates problem? How would I recognize that I'm looking at a related rates problem and I know how to handle them? So the first thing is, one, we're told about related quantities. So you would be told about, for example, the pressure and volume of a gas, right? So these are related somehow through some sort of equation. And the next thing is you're told the rates of change of some quantities and are asked to find the rate of change of another. Right? So whenever you're in that sort of situation, you know you're in a related rates situation, as opposed to some other situation that you'll see in calculus, which we're going to actually see several other word problem types. After this, we're going to cover maximums and minimums, and optimization is going to be the next big kind of word problem type. So this is how you recognize that you're looking at a related rates problem. So they're going to say, oh, you know, the pressure and the volume of a gas is related by this equation. We know that the volume is increasing at a rate of 3 atmospheres per second. How fast is the pressure increasing at some point? Right? So that, for example, is the structure of a related rates problem. So you're going to be told about how things are related. You are also going to be told about how fast some things are changing, how fast is the other thing changing. Right? Basic related rates problem structure. Now, once you recognize that you're looking at a related rates problem, the next thing you're going to want to know is, how do I solve the related rates problem? So recognize when you're looking at one. Now you want to recognize how to actually solve it. And luckily for you, I am going to tell you exactly how. In fact, I already have. In the handout that I gave you, it has 6 steps in it. And pretty much what you're going to do is you will follow these 6 steps to solve any related rates problem. So step 1 is to first read the problem very carefully. You are going to read the problem first of all to recognize that you are looking at a related rates problem, as well as to pick out useful information that's going to help you solve the related rates problem. The next thing you're going to want to do is you're going to want to draw a diagram, if necessary. Usually you want to fully understand the situation, how things relate to each other. A lot of times drawing a picture will come in handy here. And it's very typical for related rates problems for them to be problems where geometry can be very helpful. So you're going to draw a diagram, you're going to label the diagram, you're going to label it appropriately. And I'm going to talk about what appropriate means. I already mentioned it in the handout, but I'll mention it again as we're going through some problems. After that, you're going to want to write down what do you know and what you want to find. It's good to have a little target. Know what information you have and in what context it fits, usually what rates of change you know, and then you are going to actually say, determine what rates of change do I want to find, what do I not know that I would like to know. So that's the next step. The fourth step, are we at step 4? Yes. You are going to set up an equation that relates all your unknowns. So what you're going to do then is, usually the picture is going to help you out at this point. So you're going to draw a picture, and let's say, for example, your picture ends up being a right triangle. Then you know certain relationships automatically take effect, like Pythagoras' theorem, maybe, well, in this class we don't do trig, so SOHCAHTOA wouldn't ever be on the table in this class. But you get the idea. You can set up the geometry of the situation, then you're going to realize that, hey, I can use what I know about geometry to talk about this problem. So that's going to be another useful thing. Once you set up the relationship, you now have the equation. The next step would be to differentiate that equation implicitly. And with related rates, and this is probably something I should write down, the independent variable, right, meaning the variable that describes your input is always time, as in the variable is going to be, the independent variable is t, which means anything that's not a t, once you differentiate it, you are going to have to apply the chain rule and multiply by the prime. We're going to do examples, so don't worry about that. But the independent variable with a related rates problem is always going to be time. So that's the next thing. I don't even know if I'm looking at the camera or it's going to be like this video where I'm always like looking off somewhere and you're going to wonder, what is he looking at? It's very weird. I've never had to record myself. I feel very awkward right now, in case you haven't figured that out yet. Okay, so with related rates problem, the independent variable is always going to be time. Once you have the relationship, you're going to differentiate implicitly with respect to time. This is going to give you an equation that has now rates in it, because you would have to apply the chain rule once you're doing the derivatives. At this point, you can now go and you can fill in all your knowns, solve for the unknown that you want, and essentially that would be all the entire process. Now, of course, we're going to go through a lot of examples where I actually go through this process, and I'm going to explain all these steps, and we're going to really flesh them out. But again, all 6 steps are here. You will also notice on the handout that I made some of the steps in bold, and then there are some things not in bold. Basically what that is I kind of flesh out what you want to think about or how you want to look at each individual step. But of course, to have a lot of information in your head is not going to be helpful, especially in a situation where you're on a test and you need to work out a problem very quickly. So eventually what you want to do is you want to be able to just remember the sentences in bold, and because you would have read through this and you would have done many examples, just remembering the statements in bold is going to remind you of the process, and you won't get lost. You'll know exactly how to solve the problem. So read through these steps. I just quickly went through it. We're going to go through it again. And by the time you get through these 6 steps, you pretty much always do these steps in this order, so it's very important that you know these 6 steps. Okay. So we're going to do examples of us going through these 6 steps. Another thing that you're going to want to notice if you go to the next page is you're going to notice that I put in a box. Basically, what I said earlier is that geometry is going to be very convenient here a lot of the times. So you're going to have to remember a lot of your equations from geometry, like how do you find the area of a circle? How do you find the area of a triangle? How do you find the perimeter of something, right? And volumes of simple 3D figures, things of that sort. You should remember those formulas. We're going to go through some of them. But yeah, other than that, if I haven't confused you yet, let's actually just jump into some examples. Let's make sure we actually know how to deal with these problems. So that is basically, to summarize, related rates, as the name suggests, is about related rates. If quantities are related, then it turns out their rates are also related by just differentiating the relationship that we already know about. Now, why these problems are important is that if we know how fast one thing is changing, and we know it's related to something else, we can automatically know how fast that thing is changing. And that's going to be very important in various situations. A related rates type problem is the problem of trying to figure out the rates of change of some things, given that you know the rates of change of other things that are related to the thing. And in Calculus 1, and specifically in this class, you can solve any related rates problem using those 6 steps that I put on that handout. So all you have to do is make sure you know the 6 steps, know it very well. Literally every time you go through a problem, you're going to go through these 6 steps. So without further ado, let's actually go through them. Let's actually do an example. So on that handout, let's start at example 1. Why not start at example 1? Seems like a good idea. So, step 1 in any related rates problem is going to be read the problem. So, let's read the problem. Okay, so problem 1. A right circular cylinder undergoes expansion. Its radius is increasing at a rate of 1 meter per second, while its height is increasing at a rate of 2 meters per second. At what rate is its volume changing when the radius is 1 meter in length and the height is 3 meters? So, I've read the problem. First thing to notice here, now of course we're doing a related rate, so we know it's a related rates problem, but the first thing is this wasn't in a related rates packet, you should still recognize this as a related rates problem. How do you know it's a related rates problem? Well, if you read it, you'll notice that it told us about things that are related. It's talking about the radius and the height of a cylinder, and then it tells you how fast the radius and the height are changing, and then it asks about how fast the volume is changing. So we have the relationship between 3 things: volume, height, radius. It told me how fast the volume, the radius and the height are changing, then it asked me how fast the volume is changing. This is a standard kind of related rates problem. So, talks about a relationship, tell me how fast some things are changing, ask me how fast something else is changing. So step 1 is to read the problem. So now we know it's a related rates, and we're going to actually solve it. So step 2 in the related rates problem is you're going to want to draw a diagram. So your diagram must be properly labeled. In this case, it is a right circular cylinder. So I'm just going to draw a right circular cylinder, right? That just means one face is a circle and the axis is perpendicular to the base, and it's circular. Now, I explained what it means to properly label a diagram in this handout. Basically, the rule of thumb is the following. Whatever is changing, you want to label with a variable, and whatever is not changing, you're going to want to label with a constant. So here we know that the height is changing, we're told. So the height of this cylinder I'm going to label with h. I label it with a variable because it's changing. The radius is also changing. Call this r. And v, you're not going to see it on the picture, but I'm going to use v for volume here, right? So what the picture is going to help us do is help us come up with a relationship that we're going to need down the road. Now, basically what's going to happen is this should kind of start to conjure up some sort of formula in your mind the moment you actually sketch this down, and you know, you probably have like visions of high school geometry coming back to mind right now, you know, some really dark times probably for most people. So this should kind of automatically make you think of certain equations, and we'll get to the equations soon. But before we get to the equations, the third step is going to be to write down what do we know and what do we want. So what do we know here? Now, in terms of what we know, we are talking about the rates. The rates we know, and the rates we want. Okay. So, let's see, what do we know? We know the radius is increasing at a rate of 1 meter per second, and its height is increasing at a rate of 2 meters per second. So basically, I know how fast r is changing. I know the r prime and the h prime. In other words, dr dt, and I know dh dt. Right? Now, it says the radius is increasing at a rate of 1 meter per second, the height at 2 meters per second. So this is 1, this is 2. Now, there's a very important nuance that can occur here. You might have remembered a long time ago. Now it's weird. It's like if I stand to the side, which is very usual when I'm in class, now I'm out of the video and it's very awkward. Anyway, here's something that we looked at a long time ago when it came to derivatives. We saw that when something was increasing, because we see here that the radius is increasing at a certain rate and the height is increasing at a certain rate, we interpreted that as a positive slope. Derivative is a synonym for slope. So when they tell us something is increasing, they're basically telling us that the derivative or the rate of change is positive. And that's very important. So here, specifically, when they say the radius is increasing at a rate of 1 meter per second, they're specifically saying dr dt is plus 1. This is going to be important in general, right? To know that the sign of the rate is actually going to be very important to what you're doing. And also, the height is increasing at a rate of 2 meters per second. This is a plus 2, right? So that's going to be important, and that can get you in a lot of trouble, which is why step 1, read very carefully. So you have to pay close attention. When it says something is increasing versus decreasing, it's actually pretty important. Yeah. Now, what else? What do we want? At what rate is the volume changing when the radius is 1 meter and the height is 3? So what do we want? dv dt. When do we want it? Now. Well, we want it when r equals 1 and h equals 3. Okay. Now, the moment I have all this actually written down, I can actually just forget about this handout. Forget it. Just throw it away. Right? Right now, I have all the information that I'll ever need to actually finish solving this problem. I know it's a related rates problem because I read it. I drew a diagram that represents the situation. I know what I want and what I already know in terms of the variables that are in my diagram. So r is the radius, h is the height. I know how fast r is changing and how fast h is changing, and we care about how fast v is changing in this scenario, right? That's everything we need to know. The fourth step is to come up with an equation, right? The equation is going to be the relationship between all the variables, right? So I need to now come up with an equation that is going to relate my r to my h to my v. And so, like I said, when you're thinking of high school geometry at this point, you might remember that the volume of a right circle cylinder is v equals pi r squared. That's the relationship. So now, that brings us to step 5. Step 5 is to now I know the relationship pi r squared h. So step 5 is to actually find the rates that are related here. And we can get to that by actually differentiating the original relationship. Now, we're going to differentiate with respect to time. Always with respect to time. So, what is the derivative of v with respect to t? That's right, dv dt. What is the derivative of pi r squared h with respect to time? Take a few seconds, see if you know the answer before I write it down. Well, here's one thing you should notice. There are actually two functions here. There's a function of t, which is in terms of the variable r. There's also another function, h of t. What did I just say? I think I said something that didn't make any sense just now. So everyone is a function of t. We're always thinking of t as the independent variable. So r is a function of t and h is a function of t. So I have a product of two functions here, which means when we're finding the derivative of this side, the product rule needs to take effect. But you also need to remember that we're differentiating implicitly with respect to t. So every time I differentiate something that's not t, I have to multiply by its prime or its derivative. And so to differentiate the r part, leaving the h part alone, that is 2 pi r dr dt times h. So I differentiate this part and leave the h. Because I differentiated something that was not a t, I had to multiply by its derivative. Plus, now I'm going to leave the pi r squared, and I'm going to differentiate the h part. The derivative of h is just dh dt. And now I have the equation that gives us the relationship between the rates, the related rates equation. At this point now, you move on to step 6. This is where you finally start to solve the problem. You're going to answer the question here. So basically, you're going to plug in knowns, solve for unknowns. So at this point, everything that you need should already be on the board. What do we want? We want to find dv dt, which means we care about finding this guy. He's already nicely tucked away on one side of the equation. We will solve for dv dt. And I know that r equals 1. I want h equals 3. I want dr dt equals 1, and I want dh dt equals 2, and all I'm going to do now is just plug in all those guys. So 2 pi is just 2 pi, that's a constant. R is 1, dr dt is 1, h is 3, plus pi times r squared. R is 1, dh dt is 2. So dv dt is actually 6 pi plus 2 pi, or it's 8 pi. Now, in general, I won't care about the units, but in case you're wondering, this would be meters cubed per minute. Let me actually remind myself of that. Meters per second. That actually took a lot longer than I thought it would. I guess explaining to nobody is harder than explaining to somebody. Anyway, so that is the whole problem. Now, let's go over this process very quickly. We'll do a couple more examples. So, you're doing a related rates problem. You should recognize that, first of all, that it is a related rates problem, and just the problem structure is going to tell you this. You're going to be told about related quantities. You're going to be told about the rates of change of some of them, asked about the rate of change of someone else. That tells you you're in a related rates problem. Reading carefully is going to help you to know this, as well as pick out important information. Once you read, you're going to come up with a diagram that describes a situation, if at all possible or necessary. The diagrams are often going to be very helpful in you figuring out the equation. So step 2 is going to help you out with step 4. So this is something that you're going to want to do. The caveat, the thing you want to pay attention to here in step 2 is how you label the diagram, because by not labeling it properly, you can actually get into trouble here. Anything that is changing, moving, increasing, or decreasing, you're going to label it with letters. Anything that's not moving you label with its constant value. Third thing you're going to do is you're going to write down the rates that you know, write down the rates you want to find, and in what situation you want to find them. Then you're going to come with the equation. The equation is going to relate all the variables in play, and oftentimes your diagram is going to suggest to you what equation you might want to try. Once you have the equation, this is a relationship between all the quantities. You can now differentiate that relationship to get the relationship between the rates of the quantities. Once you have that, you move down to step 6. Here you're going to plug in all the values that you know, solve for what you want to find. There is a potential pitfall that can happen in step 6. Sometimes what can happen is that you'll get to step 6, but you'll have too many unknowns. You're going to realize that you don't have enough things to plug in to solve for the thing you want to find. Now, whenever you're in that situation, and we'll do some examples where we would be in that situation, what you're going to want to do is go back to step 4. Step 4 is going to be where you know the relationship between all your variables. So if you know some of them and not all of them, you can go to step 4 and solve for the guys you don't know, and then come back to step 6. But ultimately, by going through these 6 steps, you'll be able to solve any related rates problem in general. That's it. I will get out of the way for a second so you can see this beauty at a glance. But that's it. Those are the basic 6 steps for a related rates problem and how to solve it. Now, we went through that very slowly, very painstakingly. Let's try to go through a few more examples a little bit quicker. Now, since we're not meeting in person, what I would like you to do, and you really need to take this part seriously, is whenever I say, hey, pause the video, try this on your own, see what you get. It's very important that you pause the video, try it on your own, and see what you get. That is a very, 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 very muy importante, super important part of this process. It is not going to work nearly as well if you just watch the video and you never actually try anything, but you just watch me doing everything. It's not going to be as helpful as it could be. So be sure to seriously actually attempt certain things before. So I ran through that first example explaining a lot of stuff because I wanted you to have an idea of the whole process. But what we're going to do is we're going to move down to problem 3 because problem 2 is actually very similar to problem 1. That one just uses a box instead of a cylinder, actually a rectangle. What we're going to do is we're going to move down to problem 3 because that one is a little bit more nuanced, and a lot of the things that I warned you that could go wrong here will actually happen in problem 3. So we're going to go down to problem 3. So let's read that. Step 1, read. We're doing example 3. Okay. A 15-foot ladder is resting against a vertical wall. Suddenly, and without warning, the foot of the ladder begins to slide away from the wall at a rate of 2 feet per second. At what rate is the top of the ladder sliding down the wall when the foot of the ladder is 9 feet from the wall? Okay, so that's the problem. It's a related rates problem. How do we know? We're told about certain related distances, namely how far a ladder is away from the wall versus how far the top of the ladder is up on the wall. So those are related. I know how one thing is moving. The foot of the ladder is sliding away from the wall at a certain speed, and we're asked how fast is the top sliding down. Classic related rates problem. Yeah, right? So that's a classic structure of related rates problem. Now, before I tell you, take a few seconds and think about what would be the right diagram here. So pause, give yourself like 5 seconds, and then tell me what you think. A triangle. That's right. It's going to be like Blue's Clues. That's right. That's right. Okay. How do you know? Well, if I think of the wall as some vertical line, so this is the wall, the ground is going to be represented by some horizontal line, and the ladder is just leaning against it. Right? That, my dear children, looks a lot like a right triangle kind of situation, where the hypotenuse of the ladder is actually the hypotenuse of the triangle is represented here by the ladder, or vice versa. And so basically the situation here you can think about as a right triangle, right? Where this is representing the ground, this is representing the wall, the hypotenuse is representing the ladder. Now, what I want you to do is, if you couldn't get the fact that that was a right triangle, here's a chance to redeem yourself. I would like you to label this right triangle. So pause the video and take a few seconds to actually label that. Okay, so I'm going to assume you pause the video, that we're all obedient students. Okay, so let's say I wanted, you could label this anything like X and Y and Z, or A and B and C, whatever. Let's use A, B, C, right? So, did you label something like this? A, B, C. If you did, you're not following instructions. So that, while technically is not wrong, that is not a great way to actually label the diagram. Pause the video, take a couple seconds. Why isn't it okay? Okay, so hopefully what you told me or said to yourself, and we're all talking to ourselves here now, is that the key to labeling a diagram properly or efficiently is to always label things that are changing by variables and things that are constants by constants. Now, we're describing a situation. We know that the foot of the ladder, which is here, is sliding away from the wall, which means this length here is actually getting larger. It's increasing, right? So this length here is moving. So labeling it A, nothing wrong with that. Now, as this is sliding that way, we know that this, the top of the ladder, which is here, that's sliding down, which means this distance B is actually getting smaller. Okay. But what about the length C? Well, the length C is the ladder, and we're told that the ladder is 15 feet long. The ladder, it's a 15-foot ladder. It's always going to be 15 feet. Labeling with a C, superfluous. We need to label that with a constant. So we need a 15 here. Now, I'm going to mention a point where labeling it with a C could get you in trouble. Not necessarily that it's wrong, but it's a risky move for many Calc 1 students, and we don't want that. We want to get things exactly correct. So a properly labeled diagram for this situation would be that. One side is A and the other side is B, and the hypotenuse is 15. Or you can have X and Y and 15, whatever. The letters don't matter as much here. The fact is, what matters is that some things have letters, some things have constants. And the thing that's not moving, which is the ladder, should be labeled with a constant. That's always going to be 15. Okay. So that's the situation. Now, what do we know and what do we want? We are told that the foot of the ladder is sliding away from the wall at 2 feet per second, which means this is moving that way at 2 feet per second, which means A is getting larger, which means A is increasing, which means dA dt is a positive number. What positive number? Well, it's moving away at 2 feet per second. It is positive 2. And that is the only rate we have. So hopefully, when you pause the video and try the problem, you actually fill that in correctly. What do we want? How fast is, at what rate is the top of the ladder sliding down the wall? So we want dB dt. When do we want it? Now. No, we want it when the foot of the ladder is 9 feet from the wall. That is when A equals 9. Is my head blocking? Okay, so that's what we know, that's what we want. What is the equation here? Now, pause the video, try to come up with the equation. Did you get it? That's right, Pythagoras' theorem. Right? It's a right triangle. You want a relationship between all the side lengths of the right triangle. Pythagoras' theorem, right? A squared plus b squared is going to be 15 squared. That is going to be the equation that we have here. So now what we're going to do is we're going to differentiate implicitly with respect to time. This is the next step. So derivative of a squared with respect to time is 2a. Do not forget dA dt. Plus derivative of b squared, 2b. Do not forget the dB dt. The derivative of 15 squared, what's that? If you said 30 or 2 times 15, you're wrong. It is 0. So 15 squared is a constant, and we already know the derivative of any constant is 0. By the way, this is where a lot of students might actually get in trouble. I've seen it a lot. So sometimes they would have labeled the triangle like A, B, C, and therefore by Pythagoras' theorem, they would have the equation here, a squared plus b squared equals c squared. Then when they differentiate, they have 2a dA dt plus 2b dB dt equals 2c dC dt. Now, I know right now you're watching the video, and at this point, you might have the argument, well, yeah, that's fine, Jhevon, what's the problem here? Obviously, the ladder isn't moving, so dC dt is going to be 0, and so this is actually equal to 0. That is equivalent to saying 0. Here's the thing. In a high pressure situation like a test, a lot of students actually mess up on that conclusion. A lot of students mess up on that conclusion, believe it or not, right? It's something that a lot of students will actually miss. So to prevent that kind of mistake happening, what you want to do is label in such a way that you're never going to put yourself in a position to make that mistake in the first place. Why take the risk? Just label that with a constant so you automatically know that the derivative is 0 right away, and you won't need to have your mind go an extra step. Because a lot of times, students, for reasons of anxiety or whatever, it's hard for their minds to make that extra step. So don't be like that. Don't do that. So label a diagram properly with constants where there should be constants. Only label things with variables when they are changing. Okay, so that's an important piece of information. Finally now, we want to answer the question. We want to find dB dt. So what we care about is this guy right here. So in fact, I can solve for dB dt here. This is going to be minus a dA dt over b. And at this point, you're going to notice something. You're going to notice, hey, I know what dA dt is, and I know what a is. But what is b? So here, now we're in a situation where I mentioned earlier, we got to step 6, everything was going great, we labeled our diagram correctly, constants where there should be constants, variables where there should be variables. We know what we know and what we want to find. We know an equation that relates all the variables. We know how to differentiate, and we did it correctly. We remember our dA dTs because we remember the chain rule and we're on top of everything. We get to this point where we want to plug it in, finally answer the question, solve the equation, and we don't have all the information. What do? Panic. No, we don't panic. What we do is you go back to step 4. Now step 4 says, so here is where you go to step 4. Step 4 says a squared plus b squared equals 15 squared. And because I know the a is 9, and the b is, well, I don't know the b, but I know that a squared plus b squared equals 15 squared. Now, do me a favor, pause the video, let me know what b is. It should take you about 5 seconds. That's right, b is 12. Now, how would you know that? Well, the long way to do it would actually be to find 15 squared, find 9 squared. Let's do this. Find 15 squared, find 9 squared, subtract them, and then take the square root. That's a lot of work, a lot of computation. I don't allow you guys to use calculators on your exam, so probably wouldn't want to go that route. The thing to notice here is that we are dealing with a 3, 4, 5 triangle. So we know that in right triangles, the numbers 3, 4, and 5 appear together a lot. That's another thing you would have remembered from high school geometry. So 3, 4, 5 triangle. If one leg is 3, the other leg is 4, the hypotenuse must be 5, and vice versa. What happens is, by similar triangles, this is actually still true for triangles that are proportional to 3, 4, 5 triangles. So, for example, if I were to multiply this by 3, multiply this by 3, multiply this by 3, the relationship still holds. This would be 15, this would be 9, which are two numbers that we have in this situation. And so, the other side must be 12, right? So you would know that as a shortcut. So, for problems like these, 3, 4, 5 triangles is something that would be very common to test for. Another one is 5, 12, 13 triangles. So that's another one you should know about. So one is 5, one is 12, and the other must be 13. It's another very common relationship. And there are others, but those are probably the most common ones. Yeah, so through various ways, but essentially the trick is to go back to step 4. We would figure out that b is actually 12. And so this is going to be equal to minus 9 times 2 over 12 by going to step 4. And then we can simplify that a little bit. 2 into this goes 6, 3 into that goes 2, 3 into that goes 3. So this is minus 3 over 2. Now in general I don't care about the units, but let's just, this is feet per second here. Feet per second. Now, another thing that I want you to notice about this problem is, well, the fact that you got a negative answer here. Now, sometimes students freak out when they get a negative answer and they just decide to erase it or try to change the steps so that it disappears. However, if you do that here, that would actually be incorrect because that negative sign is supposed to be there. How do I know it's supposed to be there? Well, going back to the situation, reading the problem carefully, this we know is increasing, this we know is decreasing, right? As the foot of the ladder moves away from the wall, the top of the ladder moves down the wall. This distance here is increasing, so it has a positive rate of change. That makes sense. The fact that this guy is sliding down means the length of b is decreasing, which actually means the derivative of b with respect to time should be negative. So that should be a negative number here. That's actually pretty important. So I want you to notice that. That is true. Let's see, how much time do we have? Oh, a few more minutes. Let's see. So, maybe we'll go through one more example here, but let's see. what I would like you guys to try is to actually try to do all these problems. Try to do all of them within the next 24 hours or something like that, and come back to me with questions. What I'm going to do now is let's do problem 5, and we're going to run through this one very quickly. Pause the video, actually try it yourself before watching me. It's super important that you do this. It's very important. Actually pause the video, try to do problem 5. Once you believe you've gotten the answer, turn the video on again, and then see if you got the answer. Now, this problem here kind of shows you about all the things that could go wrong and how to deal with them. So labeling your diagram is going to be properly is going to be very important, and the only other situation that might be a little hiccup in the plans is you get to step 6 and you don't have all the information, and how you deal with that situation is to go back to step 4 and solve for what you need to find in order to plug it into step 6. But as you can see, I use the same template to solve both the problems that I just mentioned, and yeah, it's always these 6 steps to solve any related rates problems. So those are the important things I want you to know. These 6 steps solves any related rate problems. Step 2 is going to be super important. Not only is it going to help you come up with the equation in step 4 if it's not given, it's also important for you to label that step correctly and carefully so that you don't mess up in step 5. It's very common to mess up in step 5 if you don't get step 2 correctly. It's also very common to mess up in step 4 if you don't get step 2 correctly. So if you draw a diagram, label it properly, that's going to help you come up with the right equation, and it'll also help you find the correct derivatives, because things that would be derivatives that would be 0 would go to 0. Then when you want to get to step 6 here, filling out this information in step 3 is going to help you with step 6. Every now and then you have missing information in step 6. Whenever that happens, don't panic. Go to step 4, get that missing information. Yeah, that's the related rates problem. Let's do example 5. Let's do 5A. All right, let's actually run through this. So pause the video. I'm going to actually run through it all in one swoop very quickly, explaining what I'm doing while I'm doing it, but you need to actually try it before seeing me do the solution. Okay, so problem 5, it actually has 2 parts. The side length of a cube is increasing at a rate of 2 inches per minute when the side length is 3 inches. 5A, how fast is the surface area changing? Okay, so I read the problem, I realized it's a related rates problem. It's told me about a cube, so this is the diagram. Stop the video and try it on your own, but I'm just going to work through it now. So it's a cube, which means all those sides are the same. The length, width, and height are equal. So what do I know? The side length is increasing at a rate of 2 inches per minute. This is telling me dx dt is 2. Now you don't have to use x here. You could have used any letter, but I decided to use x. It says, how fast is the surface area changing? So we want the A dt, where A is the surface area, when the side length is 3. So now I'm going to have to come up with an area equation. Now, the surface area is just the area of all the faces. A cube has 6 faces, right? So there's the front, the back, the right side, the left side, the top, the bottom. Now, in a cube, the area of all these faces are all going to be the same. Length times width, length times width, length times width. They're all going to be x squares. There are 6 such faces with x squares, so the area 6x squared. I'm going to differentiate that with respect to time. dA dt is equal to, well, 12x dx dt. And now I can just plug in my knowns, solve for my unknowns. I want dA dt, so I don't know what that is. So this is going to be 12 times x, which is 3, times dx dt, which is 2. That's it. So that's 12 times 3, 36 times 2, what is that, 72 inches squared per minute. If you don't write that, I don't care. But that's it. That's the problem. See? Moves by very quickly. Goes by quickly when you know what you're doing. I actually believe time is up now. Didn't know exactly when we started, but I think we've been going for about 50 minutes. Let's run through B really quickly. Why not? What, you got somewhere to be? No, you have nowhere to be. Of course. How fast is this volume changing? So this is B. Pause the video. But let's actually run through it very quickly. Let's go through it from scratch, even though it's the same kind of problem. Okay, so let's start over. The side length of a cube is increasing at a rate of 2 inches per minute. When the side length is 3 inches, how fast is this volume changing? Diagram, cube. So it's like a box where all the length, the width, and the height are the same. What do I know? Well, I know the side length is increasing, which means it's plus 2. What do I want? I want the rate of change of the volume when the side length is 3. I need an equation that relates the v to the x's. The volume of a box is length times width times height, so that's x cubed. Now, that means dv dt is going to be 3x squared dx dt. So dv dt is going to be 3 times x, which is 3 squared times 2. So that's 3 cubed, which is 27. Geez, I wish I had students here to do arithmetic for me. And then I take the 27 times 2, that gives me 54. And it's volume, so it's inch cubed per minute. But if you just told me 54, the volume is increasing at a rate of 54 cubic inches per minute. Try some of the others. I'll probably, but maybe not, depending on the questions I get asked. Try the others. Some good problems to try. I would do problem 2. I would do problem 6. I would do problem 7. Problem 8. Problem 9. Problem 10. I probably won't ask a question like problem 11. You can do that if you want to get extra practice, but that's problem 11 is probably not something I would ask. But pretty much everything besides problem 11. Try it. If you have any questions, let me know, and I'll see you in that next video. So this was awkward, but hopefully that worked.